let us solve one of these problems using virtual work method. Okay. The problem is that of a 2-bar truss pinned at both ends. Okay, let us call this as A, B, C, and a force acting like this, let us say 50 kilonewtons. Okay. Now, so each of these bars is 1 meter and the distance between them is 1 meter. Okay. This is a problem that you can solve by using simple equations of equilibrium, right. Now, is this a body or a system with enough number of unknowns and number of equations? Let us examine. If we remove this joint and this joint, these are two supports with respect to fixed frame of reference. If we remove these two, we have 4 unknowns appearing, 2 unknowns here and 2 unknowns here, and we need to solve for those 2 unknowns. If you look at this particular system, this system has 1 degree of freedom. Okay, that is not very difficult to understand. I can fix one of these and then see whether the other bar is moving. The other bar can rotate about this particular bar, which means there is 1 degree of freedom. If there is 1 degree of freedom internally here, I can generate 3 for the rigid body plus 1 using the 1 degree of freedom, which means 4 equations can be formed and we have 4 unknowns, we can solve for them. Okay. So, in that sense this is a determinate structure, meaning I can always find out the unknowns using just purely equations of equilibrium. Now, one of the important things to note here is, if I ask you how many degrees of freedom does this system have with the supports, which means that if I have 1 degree of freedom here, have I arrested enough degrees of freedom for it to be stable, or in other words cannot move at all? The answer to that question in this particular case is yes. Okay. So, if I ask you the system degrees of freedom, this is with fixed points, the number of degrees of freedom is 0, alright. Supposing I ask you the same question by removing this, how do you go about finding out the number of degrees of freedom for a system? This is the first and foremost important thing that you have to do in the virtual work method. Okay. Let us take this particular example, because we can find out the degrees of freedom. There is no support here, there is one support here. How do we go about doing this? We will resort to how we did in the earlier sections. We start with the fixed frame of reference. This is completely fixed, right, and we know that there is a pin joint over here. So, let me draw it separately. I have these 2 members, there is a pin joint here, there is nothing over here. If I remove the fixed frame of reference and look at this particular free body, we have 2 unknowns that come into this, or in other words, this, by releasing this, there are 2 degrees of freedom that you release. Okay. The 2 degrees of freedom that you release are this direction and this direction movement. Okay. To put it the other way, the fixed frame basically freezes this point from moving in the 2 directions. The 2 directions can be x, y, or x prime, y prime, and so on. We have already done that. Okay. So, the body lost 2 degrees of freedom by fixing it to fixed frame of reference. Okay. Individually, this particular rigid body has 3 degrees of freedom, meaning it can move without bothering about any of the other constraints. This can move with 3 degrees of freedom. This is something that we know, and I am just talking about the planar rigid body here. Okay. So, I have -2 over here because there are 2 that are lost by fixing. There are 3 degrees of freedom for this, and if I fix this rigid body also to the fixed frame, I know this can rotate about the point B, which means this has 1 degree of freedom with respect to this. So, I am going to write 1 here. So, I will repeat this. I look at this rigid body, it has 3 degrees of freedom. If I fix this rigid body and look at what is happening to the other rigid body can have 1 degree of freedom, which is rotation. So, I put 1 here. Apart from that, this particular rigid body has lost 2 degrees of freedom by fixing it to fixed frame of reference, and therefore, the total degrees of freedom that this body can have is 2. Right. And in this earlier problem, we knew that there are 2 degrees of freedom that we arrested here. When we did that, this comes down to 2 minus 2 equal to 0 degrees of freedom. Okay. And this is an essential part in this method of virtual work. Okay. You need to find out the degrees of freedom of the particular system. Okay. Supposing I want to solve this particular problem with 2 bars pinned together with a hinge support at both ends, we know the degrees of freedom is 0, which means I cannot solve this problem directly using virtual work method. I need to release at least 1 degree of freedom, okay, and that 1 degree of freedom can be associated with the kinematics or the movement of the structure. So, please understand that in virtual work method there has to be movement possible, okay, in which case supposing, let us ask this question, what do I want to find out? Supposing I say which one do you want? Tell me something that you want to find out. Shall we say reaction, vertical reaction here? Okay. The task is to find out vertical reaction at A, let us say, alright. Now, please remember the fixed frame of reference will react because it is constraining the vertical movement, and therefore, there will be a vertical reaction coming in. Okay. Supposing I release that and apply AY, which is the reaction, it is one and the same, okay, at equilibrium. Okay. Please remember the two are different in terms of movement. I will repeat this once more. Supposing I release this and let it have a vertical degree of freedom and I apply a force AY, is this body in equilibrium? The answer is yes, if I have found out AY properly. But is it kinematically stable? Not really, because it can move, even a small disturbance is enough for it to move. Okay. Whether it is a stable equilibrium or unstable equilibrium is another story to find out. But in this particular case, if we seek to find out, let us say AY, we need to release that particular degree of freedom or that displacement. Okay. And once we do this exercise, we know the number of degrees of freedom for this body is equal to 1, alright. What is this degree of freedom? Vertical movement. Okay. So, let us say the vertical movement I am going to call as delta y at A. This vertical movement is such that the body is in equilibrium. Okay. Slight virtual displacement of this will give us an idea of the equilibrium of this body. That is the idea of virtual work principle. Okay. So, let us move on and find out what we should do next. Okay. One more important point before moving. What do I mean by this degree of freedom, sir? It is not very clear to me. Okay. So, I am going to make it clear by giving a simple example. Let us say I have an equation Ax, let me just give numbers, 3x plus 4y equals 7. Let me add one more, plus 7z equal to 2, 5x plus 3y plus z equals 7. Let us say I have these two sets of equations. Let us say unknowns are x, y and z. Okay. If I ask you the question, how many degrees of freedom this set of equations have, is the question very clear? But if I ask you, can you reduce this in such a way that you can write one equation in terms of one of the variables? Let us see if we can. From the first equation, I can write z equals 2 minus whatever in terms of x. So, it is, let me write it as 3x minus 4y divided by 7. What I have done here is I have written z in terms of x and y. If I substitute over here, z is eliminated and we have an equation that is in terms of x and y. Now, we have reduced, supposing I am not using this equation, I have inserted that into this, we have reduced this equation into having only two unknowns. Is this clear? Let us do that exercise because that will be useful to us. So, let me do that reduction, 5x plus 3y plus 1 by 7 times 2 minus 3x by 7 minus 4y by 7 equals 7. This is what we have. Okay. Let me just regroup fast. 5 minus 3 by 7x plus 3 minus 4 by 7y is equal to 7 minus 2 by 7. Is this okay? If you notice here, this is an equation in terms of x and y. Now, can I ask this question? Can I write y in terms of x? The answer is yes, right. So, in this particular case, even though I have two unknowns, I can write one of them in terms of the other. Let us say I am going to put x is equal to some arbitrary a. Can I write y as a function of a? Again I will repeat this. If I say x is some parameter a and I ask you, can I write y in terms of a, can I write z in terms of a? The answer is yes, right. This parameter essentially is the backbone of these two sets of equations. Okay. In this particular case, that parameter is nothing but x, or in other words, I can write everything in terms of x. Y as well as z can be written in terms of x. Okay. So, this two set of equations is a single parameter family, okay, and this we call as one degree of freedom. I can give you the value of a and you can find out x and y. If I give a different value of a, you will get different value of. I have the freedom to give you the value and you can find out the other variables. Okay. Supposing I give one more equation, okay, which is independent of this, then I know the number of degrees of freedom is 0 because everything has a single value. I could have solved for x, y and z. Supposing I had not given this at all, then I have this equation. Do I have this equation? Answer is no, I do not have this equation. I have one single equation, as you can see over here, right. What is Z a function of x and y? Unless I give you the value of x, unless I give you the value of y also, I cannot find out Z. This directly means that there is a 2 degree of freedom system. So, if I give a system and you are able to write only one equation like this from equilibrium, then I can say that I have a 2 degree of freedom system. So, in this particular case, when I say 1 degree of freedom system, it means that there is one movement that I do, every point of this body, can be, the movement of every point of this body can be found out using this 1 degree of freedom. Okay. So, let me write it down so that it is easy. So, on specifying the value or values of the degrees of freedom, DYF is a short form, okay. The movement, moment is different from movement of every point of the system. I can also write this as particle, okay, of the system can be determined. This is very important. This is what we call as kinematically admissible displacement. Okay. For example, in this, if I move this guy, every point of this would have moved. Okay. I am going to show that in a simple example. And therefore, if I have to find out how much this has moved, 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 all these will be functions of, will be in terms of delta YA. Is that clear? Of course, this point we already know, it is equal to 0, displacement of this is equal to 0, and therefore, since I can find out the displacement of all these with respect to delta YA, this one supplying a single value of delta YA, I can find out the displacement of the entire system, and therefore, degrees of freedom is equal to 1. Supposing it were 2, I have to specify the values of 2 of those, and then I can find that out. Okay. Is this clear? And this is the first exercise. After finding out the degrees of freedom, you also have to tell which one is the degree of freedom. Okay. Here lies the trick. There are many ways in which you can do this. Is it necessary that it has to be delta YA that has to be the degree of freedom? Not necessary. Remember, if I specify this, can I find out this? Let me ask you this question. I have written 2x plus y is equal to 7. Let us say this is the degree of freedom. If I specify x, can I find out y? Supposing I give you y, is it possible to find out x? Or in other words, if I give you displacement of any other point, I should be able to determine this, which means every other point also is a candidate for degree of freedom. Please do not misunderstand what I am talking about. I can choose any one of these displacements as the degree of freedom. All the other point, the movement of all the other points can be determined using that particular degrees of freedom. There are several options. For example, I can take the angle between this. The angle is changing. Okay. If I specify this angle, then every point of this can be found out. Okay. So, it is a matter of choice, and the moment we have choice we also have a problem, which one, right, and that is basically is the crux of the problem. Many times we do not recognize, okay, this is a degree of freedom that I can use, okay, but any one of them that you have used you will get the proper kinematically admissible displacement. Okay. After having found out the degrees of freedom, you also need to find out the next step of finding the active, mind my words, active forces in the system. Okay. What do I mean by that? There is no cancellation that happens, or there is no internal force that takes part in this virtual work method. For example, here I have a 50 kilonewton. Let me just change it a little bit so that it is easy for you to comprehend. Let us say there is only the self weight, okay, for which I want to find out. There is a self weight here, I am just using the center of mass here. So, this is mg1, mg2. In this particular case, since they are same length and let us say mass per unit length is the same, I will write it as mg acting at the center. Okay. Now, it is very clear, the external forces Ay, mg will take part in the virtual work equation. Now, how about the reaction at B? One of the confusions that happens in this virtual work method is which force should I take, sir? Please remember, only when I remove the pin that joins the two bars, I will reveal a force and an equally opposite force that are internal to this particular joint B. Okay. The moment I have one force and another force opposite to each other and there is a displacement, the net force there is equal to 0, or in other words, it does not matter what reaction the bar AB offers on BC. Okay. I will not have to bother about it. This is the beauty of virtual work method. So, very simple, active forces involved in this particular case, since I have released this Ay, mg and the other mg. Mind you, here also I do not have to bother about the reaction. The reason is there will be equal and opposite reaction and the displacement will come into play. Here one more important point is the displacement is equal to 0. So, in the virtual work method, if either displacement or the force is equal to 0, the virtual work is equal to 0, and therefore, it does not take part in the equation. What does virtual work principle say? The total virtual work due to a small displacement given for the degree of freedom is equal to 0. That is the statement that we will be using effectively here. But before that, mind you, for supposing I use this delta Ya as the displacement given to me, I have virtually moved this point A vertically by delta Ya. For now, let me just remove this delta Ya and all those, because it is just one value that I am looking. So, I have moved it by delta. What are the other things that I need to find out? I need to find out the kinematically admissible, or in other words, what happens when I move this delta at these 2 points. Okay. How much do they move vertically? If I know that information, I have solved this problem, because I just need to use those and write down the virtual work principle. So, the next set of values that I need to find out are finding the virtual displacements along the active forces. Okay. Once I know that, it is pretty simple. let me just number these, name these, let us say this is P, this is Q, okay, A, B, C, P, Q, okay. So, if I have to write the virtual work equation, the virtual work equation will be AY times movement in the same direction as movement in the same direction of this force will give me a positive virtual work, right. So, I need to be bothered about the directions of both the force and the displacement. If they are along the same direction, it is positive. If they are opposing each other, it is negative, okay. If it is both same directions, it is positive, okay. So, this is something we have to understand. So, if I have to find out this and this, first let me write down the virtual work due to AY, then I have mg is acting downward, okay. Let me draw this over here so that it is easy. This has moved over here, let us say this is the displacement, this is delta, there is a AY acting like this, there is an mg acting like this, there is an mg acting like this. Let us say this movement in the upward direction is delta p, okay. This one again in the upward direction is delta q. Mind you, movement upwards, force downwards. So, I will have mg minus mg times delta p, similarly plus minus mg times delta q, and this should be equal to 0, okay. And this gives me AY delta plus, I am sorry, minus mg times delta p plus delta q equals 0. This is the virtual work equation. If I find out delta p and delta q in terms of delta, let us say let delta p equal to, let me just give some number p times delta, okay. Similarly, delta q is equal to q times delta. This p and q I need to find out from kinematics, alright. If it is so, I can insert these into this, I will get it to be AY times delta minus mg times delta p is p times delta, delta q is q times delta equals 0. You can see that delta is common throughout or in all the terms. I get del AY minus mgp minus mgq equals 0. What do I know about delta? Delta is a non-zero displacement that I have given, which means this has to be equal to 0. So, what I get is AY equals mg times p plus q. Alright, is this clear? What is left out is how do I find out delta p delta q. The moment I find those two out, then I have solved this problem for AY. Is this clear so far?